Hi and welcome to the Transmission Electron Microscopy Lab. As you can see, the microscope contains a lot of different knobs and control panels. On the bottom you also have pedals. The pedals you use to tilt the sample in different directions. To position the sample across and change the view of the sample that you are viewing, you use these two knobs. These you can turn and then the sample will move. This column contains vacuum, and on the top here we have an electron source. This electron source shoots electron straight through inside this column. And at the midsection here we put in our sample. The electrons passes through the sample and interacts with the sample. Thereby they continue downwards the column and hits a fluorescent screen at the bottom here. If you compare this to a regular light microscope, you know that a regular light microscope has its light source at the bottom and you view from the top. Here it is sort of the reversed case. The source is at the top and you view at the bottom. And that is a practical reason, because otherwise you would need a ladder to stand up and look on top of here. So now you can sit easily on a chair beneath and study your sample. When you do TEM analysis, you usually put your samples on small metallic grids. And these grids you buy, and they usually come in a box that looks like this. So here you have several small holes, and in each hole there is a small little of these metallic grids. If you open the box, then you can pick up one of these, and then you can see that it looks sort of like this. Very tiny little dish. This dish is sort of 3 mm across. Here you can see the metallic dish in a much higher magnification. This is my tweezer again. As I said before, the diameter of this is 3 mm across. And you actually can see, perhaps in this movie, that there are small holes in this mesh. And the size of those holes is determined by the mesh number. So you can buy grids of different hole sizes. Usually these grids are not only holes. Usually the holes is covered by some kind of film. Most commonly is a carbon film. This is how it looks like from the other side. One side is dull and the other side is glossy. If you have, for example, a solution-based particle that you want to study, nanoparticles of some sort, then the easiest way is to just drop the solution onto this grid. Then the particles will stay on the carbon film and they will be easily monitored in the TEM. To put the sample inside the TEM, you need a sample holder. Here you can see 4 of them. The first one is a very basic sample holder. Here in front is the piece that goes inside the vacuum. You can see the O-ring here that separates the atmospheric pressure from the vacuum. Inside here you can see there's 2 sample slots where you put in your samples. And you just clamp them with this little clamp, and that fixates the sample. This sample holder is, instead of the previous one with the clamps, it only has 2 screws. So here you need to have some pre-configured sample that you can screw and attach with these screws. These are usually used for metallic samples that are polished down to the required thinness. The third sample holder only has 1 slot for the sample here. But this is a much more advanced one, because if you look downwards on the top here of the holder, you can see it has an electric motor that actually can tilt the sample. So by using this holder you can tilt this sample in 2 orthogonal directions. That means it's much more suitable for crystal analysis. This is the final sample holder that I'm going to show you. This is a much more advanced one. Here you have actually a moving probe in top of here. This probe you can in situ probe and contact the materials. Here you don't use these grids, but the sample is instead glued to a small metallic wire that you see here here in front of the holder. So here I have the sample holder. The samples have already been mounted at the top here. We insert this sample holder in the side here at the midsection of the column. The vacuum will start to pump, and this usually takes a few minutes. So now when the air has been evacuated in this pre-chamber, we can rotate the sample and gently insert it inside the microscope. Be careful though that you continually hold and grab the holder while you insert it. Otherwise it might go too fast inside and actually hit something and destroy that. The electron source at the top here in this particular microscope is of thermionic type. That means that the electrons is generated by heating a filament. Thereafter the electrons are accelerated in this gun section, and the accelerating voltage in this system is between 80 kilovolts and 200 kilovolts. If you have thick samples that's sort of hard to penetrate, you need to have a higher voltage. These three knobs are apertures. And the first one is a condenser aperture where you choose the size of the beam. If you use a small spot size of the beam, then you lose intensity, but you also increase resolution. The midsection aperture is an objective aperture. With this aperture you can select out and filter out the electrons that are deflected in the sample. You do this to increase contrast. You can also use this objective aperture to instead only select the deflected electrons. By doing so, you create a dark field image instead of the bright field image. The bottom one here is for electron diffraction. This aperture, you select your region of interest on the sample. And by doing that, you can choose what region you want the electron diffraction pattern to occur from. At the bottom here you have the viewing screen. That is basically a fluorescent disc, so when the electron hits the dish, it glows. And then you can see that with your eyes. So either you view this just by your eyes manually, or you use these binoculars, or perhaps the most common thing is to use a camera. Here we have a very simple camera that is just filming this fluorescent screen. Alright. The starting procedure to start up the TEM after you have inserted the sample into the column, that is to check that the vacuum level is correct. After you have checked that the vacuum level is correct, you start by decreasing the accelerating voltage setting down to 100 kilovolts for this system. After you have reached 100 kilovolts, you turn on the high voltage setting. Then you check here on the meter the beam current value. This is the dark value as it is called. And this should be roughly half the value of accelerating voltage. The second step is to increase the accelerating voltage. And we do that in steps of 10 kilovolts. And we continue that until we reach the settings of voltage that we require for the experiment. Now I have reached 160 kilovolts. And I can see that the beam current here shows 81, and that's okay. The next thing is to turn on the filament. We do that by turning on the filament knob. And here it is important depending on what kind of source you have for the electron. If it is a basic tungsten filament, then you can turn this knob up all the way with a constant slow motion, half a minute turning. If instead you have a Lab 6 crystal filament unit, then you must heat that much more slowly, several minutes. Otherwise, if you heat up it too fast, the crystal might crack in its soldering against the filament wire. So this is the viewing screen in the microscope. You can also see that there are two screens. One smaller dish atop of the bigger one. The smaller dish is used for the binocular view and the camera view in this setup. For the current demo session, we turn off the small dish. So now we only have the big dish that exposed to the electron. I shall turn off the light in the room. The green regions you see is the fluorescenting behavior of the fluorescenting screen when it's hit by electrons. You see there are green squares, and if I translate the sample, you see that there are these repeats. So the black bars in the picture are the copper mesh of the TEM grid. So the actual sample that we're going to look at is these small tiny black dots that you see inside these squares. So we're going to select a nice square, and then we're going to focus on that and magnify it. So now I have a magnification of 4000. And the small pieces you see in the middle of the screen, that is the molybdenum trioxide crystals. So now I switch to the camera view, which you will see on the screen now. So the green has now becomes gray. And the black region here is the sample that's being observed. So this is the molybdenum trioxide crystal viewed in the TEM camera. What we have here is 4000 in magnification. And you can see with the scale bar on the screen that the width of this is sort of almost 2 micrometer. Now watch what happens when I turn the focusing knob. If we want to make electron diffraction out of this, then we use the selected area aperture. And then we select the region of interest. Go to diffraction mode, and you see the diffraction pattern. And molybdenum trioxide is almost simple cubic in its structure. So we suspect to see some kind of square-shaped pattern, as we can see in this image. I want to create a dark field image. What we do then is we put in the objective aperture and chooses the spot in this diffraction image that we want to create the dark field image from. Here I put in the aperture. You can see it sort of selects out a few diffracted dots and the central beam as well. We choose a smaller one. Now I choose a smaller aperture, and then I move it so it only contains a few of the neighboring dots. Let's say these two. And then we go back to the default imaging mode, and the dark field image shall appear. So this is the dark field image. Here the white represents those electrons that was diffracted into that little aperture slot that we selected. Here is the standard bright field image again. I told you that the contrast in the image could be enhanced by putting in the objective aperture. We can try that. You see? The black things becomes more black. That means that the electrons that were deflected in the sample now has been filtered completely away, and it never hits the fluorescent screen. You can increase or you can reduce this effect by choosing different sizes of the aperture. And then we're back at the beginning. Now I have turned on the lamp again and put back this protective cover screen. So how to shut down the microscope, you basically do the reverse procedure of starting it. So first you turn off the filament. After that you go down to the 150 kilovolts in accelerating voltage. Then you turn off the high voltage. Turn off the computer screen. And that's it. Then we are ready for the next